Hello, welcome to the screencast. I want to talk a little bit about respiratory physiology 2A and the exchange of gases at the tissue level and at the alveolar level here. And some of your time writings were showing that we need maybe need me to go over this a little bit more. So let's talk about the PO2 first here. So let's concentrate on what the PO2 is in the alveolar spaces. So you see these bars here. The unit on the bars for these little graphs is millimeters of mercury. And so for the inspired air, we know that the level here is about 152 millimeters of mercury. But by the time it gets into the alveolar spaces, it is at about 105. So the PO2 inside the alveolar spaces is about 105. Now this is where people are getting a little confused, and most of you understand that it seemed to anyway, that the PO2 you're going to have diffusion happening from high levels of PO2 to low levels of partial pressure of oxygen of PO2, so that this is the direction of the diffusion. So that means that in order to get oxygen to diffuse into the pulmonary capillaries right here, the PO2 in the capillaries had to be lower than the PO2 in the alveolar spaces. But what was seeming to be confusing is that the blood is constantly moving. So we've got blood coming into the alveolar capillaries. So this is blood entering the alveolar capillaries or the pulmonary capillaries, and then blood leaving the alveolar capillaries or leaving the pulmonary capillaries. So the blood that's coming in has a different PO2 than the blood that's leaving the pulmonary capillary beds where the exchange is happening. And that, of course, is due to the partial pressure gradients, but the blood moving is more rightly due to this right ventricle, right, contracting, undergoing systole, squeezing blood into that pulmonary circuit, and then returning it back to the pulmonary veins, or via the pulmonary veins to the left atrium there. So if we look at that PO2 that's entering the alveolar capillaries, it is at about 40, right? So this bar is lower than this bar on the graph. So that means that if you had a PO2 of 105 versus 40, the oxygen would then be diffusing down its partial pressure gradient from the alveolar spaces into the blood. Now, as we know, diffusion happens until a dynamic equilibrium is established, and this happens relatively quickly. So it's about 0.25 seconds that the blood spends in that pulmonary capillary bed. And by the time it comes out, you have equalized the partial pressures of O2. So the level on this over here is 105. So if you had a PO2 of 105 versus a PO2 of 105, you'd have no net movement of that oxygen. Now, since the right ventricle is contracting, undergoing systole, is squeezing, pushing that blood all the way through the circuit there, the left ventricle then is going to be pumping that blood, that oxygen-rich blood, this is the left ventricle, pumping blood into that systemic circuit, right, around here. So now the opposite is going to happen at the systemic capillaries, right? So again, blood entering the tissue capillaries is the systemic capillaries, as I call them. And again, that is going to be about 105, that value. And then inside the cells, however, the value is going to be something that's less than 105, and it depends on where we measure that. Inside the cell, we can measure it inside the mitochondria. It's going to be really low there because, of course, remember that in cell respiration uses oxygen and produces CO2. So if the cell is using oxygen here, the PO2 is going to be relatively low. So we're just going to call this, for right now, 40. Right? So again, if you're going to compare 105 versus 40, you know that the oxygen is going to diffuse down the gradient here. Now you look and see that these values are the same up here as up here, but the direction is different. Here, the direction of diffusion is into the blood. Here, the direction of diffusion is out of the blood into the cells. Right? But the values, let's keep the values the same there. So then, as that blood comes in, it's got a PO2 that's relatively high compared to the cells, and so that oxygen diffuses into those cells across the capillary bed. The oxygen that's leaving, blood leaving these systemic capillaries here, is then going to be at about PO2 of 40, right? Because this went to equilibrium, so 40 versus 40, there's no net movement here. But of course, if that blood was stagnant, if it wasn't moving through this systemic circuit, then you dump off oxygen, but then you wouldn't get any more oxygen diffusing there because it would have gone to equilibrium. But fortunately, that left ventricle is continuing to undergo systole and pumps that blood, right, back through, and you get venous return here, which we discussed before in terms of increasing cardiac output, etc. So then you have that venous return bringing that deoxygenated blood back to the right ventricle. That right ventricle undergoes systole and then returns that blood that's at a PO2 of 40 back to the alveolar spaces there for exchange. So that is the oxygen, right? So let's just go here a second, and we can then put some values on here. So the PO2 in the atmosphere, we said was about 152. In the alveoli, it's about 105. This is EPC. This is entering the pulmonary capillaries. That's at about 40, right? And so we'd see that then we have, we have the movement of this here. So by the time it's leaving the pulmonary capillaries, it's at 105, right? Entering the systemic capillaries, it's at 105. Leaving the systemic capillaries, it's at about 40. Well, where did that difference go? That then diffused into the tissues, right? So the tissue level there is somewhere 40, and inside the mitochondrion, it's going to be as low as 5 to 2 because the mitochondrion is where the O2 is being used, right? And so this 40 that leaves the systemic capillaries returns back here and is what's entering the pulmonary capillaries, right? But then you have the diffusion of this entering the systemic capillaries, right, this way, and then that oxygen is going to continue to diffuse this way into the mitochondria where it's going to be used, okay? So just a way to kind of graphically organize that. Let's go back and talk about CO2 here real quick, and then we'll end this. So then I think the easiest way to do this is to separate the O2 from the CO2. Don't try to describe everything at once, right? So I'll just switch colors here. But the same concept is going to hold true, right? Let's start down here in the tissue cells where CO2 uses, cell respiration uses O2, but it produces CO2. So that means that the PCO2 here is going to be about 46. That means that the blood that's entering the tissue capillaries has to have a PCO2 that's lower than this 46, right? And it turns out that it is. It's at about 40, right? So if you have 46 versus 40, the oxygen is going to diffuse down its partial pressure gradient and go this way. So that's why we see carbon dioxide diffusing into the capillary beds here. The blood then that's leaving the tissue capillaries has a PCO2 that's about 46, right? So again, 46 versus 46 would be at equilibrium, and you wouldn't have any movement of carbon dioxide there, which is a good thing that the blood is continuing to move, that this left ventricle is doing its job here and keeping that blood moving past those systemic capillaries. Return that deoxygenated blood, right? High PCO2, relatively high PCO2 here. This enters the blood entering the pulmonary capillaries then is at about a PCO2 of 46. That gets to the pulmonary capillary beds, alveolar capillary beds, where inside the alveolar spaces that PCO2 is at about 40. And so now we have 46 versus 40 again, and we're going to see that moves down its partial pressure gradient. Right? So again, but here the direction is different than it was over here. Here it's from the cells into the blood. Here it's from the blood into the alveolar spaces. External respiration. Right? So then the blood that leaves the alveolar capillaries or the pulmonary capillaries there is at about a PCO2 of about 40. Right? And then that blood that leaves enters the left ventricle, comes out of, or left atrium, left ventricle, comes out into the aorta, and then returns to the tissue levels here again, where it's that PCO2 is about 40. Right? So if we track this, let's start at the other end here. The carbon dioxide is not produced in the mitochondria, and it's produced in the cytoplasm of the cell itself. So that's at about a PCO2 of 46. The blood that's leaving the systemic capillaries is at about 46, but the blood that was entering was at about 40. Right? And so the blood that's coming in, you had this diffusion of carbon dioxide into the blood this way. When it left the systemic capillaries, it was 46. That means that it's entering the pulmonary capillaries here at about 46. It's going to leave those pulmonary capillaries at about 40. Okay? And so where did that go? Well, the alveoli here was about 40, so that diffused into the alveoli there. And when it gets into the atmosphere, this is somewhere around the high 20s, right? So this again will diffuse this way. This is what you actually exhale, right? And we'll talk about that exhalation and inhalation in another screencast, right? So just again, kind of graphically organizing, putting the values on this here to help you talk about the exchange, the partial pressure gradients. And again, I would highly recommend sort of separating the oxygen from the carbon dioxide. Don't try to talk about them all at the same time. Okay, thanks for listening. Hope that was helpful.